So we start with the short course, and here we are starting with Kathrin. So interestingly, Kathrin wanted to be an archaeologist. So where is it? Come on, go. Yeah, here it is. So sorry, I'm taking more time than what I was supposed to do. So, but she became a space researcher and a principal investigator of Rosetta. Rosetta is one of the few instruments of Rosetta that stand really out. And the science that we got from Rosetta is spectacular, okay? And not only spectacular, that is actually it opened ourselves more into understanding comets. So without saying further, I ask Kathrin to take the stage.
I'm actually used to give lectures on Monday morning at 8 o'clock. That's when the pure students of medicine had to take physics, which is rather... But today I don't tell you about basic physics. I tell you about what we learned from studying a comet, from studying 67P, about the evolution and formation of the solar system. You know, Rosetta is called Rosetta because of the Rosetta Stone. The Rosetta Stone was found by the troops of Napoleon in Egypt. They stole it and brought it back, first to Paris and now it's in London. And this stone has in 3 languages, in hieroglyphs, in Egyptian demotic, and in Greek, the same text. That was the first dictionary on Earth, and this helped to decipher hieroglyphs. So the inventor of Rosetta thought that Rosetta has to do the same, studying one tiny little comet and then decipher the history of the solar system from that one. This is a rather large goal, I would say. And we did that, we tried to do it by just starting from the chemical composition. So each species we detected tells its own story, be it deuterated water, be it atoms like xenon, be it organics. Each species actually is unique. If we look at the evolution of the solar system, we probably have to start somewhere in the interstellar medium. From the interstellar medium, we go through the stage of a molecular cloud, then to the star-forming region, protosolar disk, then protoplanetary disk, finally to our solar system, evolution of the solar system, and in the end, to the origin of life. What happens here in all these stages is chemistry. And you start out really in the interstellar medium with chemistry. These are your starting conditions, and then, of course, the physical conditions will play a big role. You need to know the density, you need to know the physical conditions, temperature, time, also ionization degree, and so on. And then the rest is just happening, more or less. In order to study this, we had the Rosetta instrument on the Rosetta spacecraft. It was not on the lander, it was on the spacecraft. And it was designed to measure the volatile material of the comet. So what comes off the comet. We didn't investigate dust, we didn't investigate ice directly, just the sublimated species. Rosetta actually has 3 sensors. You see DFMS. DFMS is a magnetic double focusing mass spectrometer near Johnson configuration. A classical mass spectrometer, the weight is approximately 15 kilograms. And it's actually a high precision instrument. It has a mass resolution of roughly 9,000 at mass 28 on the 50% level, or 3,000 at the 1% level. And that's unique in space. I think never before was an instrument flown with that mass resolution. And the typical mass spectrum looks like this. That's mass 14. We measure one mass after the other. We cannot measure everything together. We have to step through. And you see here N, you see the CH with the 13C, and you see the CH2 with the 12C. And we can separate all these peaks. Then we have the time of flight instrument, RTOF. It measures much faster than DFMS because it can get every mass at once. It has a high mass range. It also has a good sensitivity. And it's also about 15 kilograms. And then we have, that's a typical spectrum of RTOF. And then we have COPS, the Comet pressure sensor. That was a very useful instrument. It just measures total density, as you do in the lab in the vacuum chamber. It also measures the ram pressure. If we go back, the gauge pointing upwards points to the comet. That's a closed gauge, and with this we measure ram pressure, and the other gauge is over the edge of the spacecraft in the free flow of the gas. It measures total density, and from that we get dynamics. But the navigation also got the wind from the comet to navigate safely around the comet. And finally we have the DPU, data processing unit. Of course, this instrument was built in the 90s. It's not the Pentium, it's a 386, but it doesn't have Mac or Windows, so it worked perfectly. When we arrived at the comet, we saw very soon that the coma is extremely dynamic. The gas coming off the comet changes with time. It changes according to where the spacecraft is. And you see here, we have, that's COPS, that's the total density. It varies factor 10 or more. And it's related to the rotation period of the comet. Because sometimes what you see is a small area where gas comes from. It's a duck. If you look at the head, the area is small. If you look at the broadside of the duck, the area is large. And then you look at the bottom, it's small again. And that's what we see here. So that's the rotation period. And here we were over the summer hemisphere, which was in the north at that time, and here over the winter hemisphere, which was in the south. So more gas in summer than in winter, which makes completely sense. Other instruments also measured, like the Wirtis, the infrared, and they found out that water comes from one side and CO2 more from the other side. So it's also heterogeneous, the coma. It's not only variable, it's also heterogeneous. The plasma instruments also measured, and you see here, this here is COPS, this here is the LAP, the Langmuir probe. They are correlated, the plasma and the neutral gas. Then later on we experienced some diamagnetic cavities, but not like at Comet Halley, where we went into the diamagnetic cavity. Here it was a very fast thing, a few minutes, and then we were out again. And finally we had the singing comets. We had a lot of plasma waves, which you can turn into music if you like. So it's not just measuring composition, it's measuring dynamics of the coma. I take you now to a visit to a Sioux. It's not the Sioux of San Diego, it's the Sioux of 67P. I'm not a chemist, I have to confess, I'm a physicist. And as such, I always have problems with organic molecules. I forget how they are called. I forget where the double bonds are, if they are branched or not. So I had to do something for me, and I invented the Sioux. This Sioux is of course based on water, because that's by far the major species of the volatile in the comet. Now this water has some fish here. It has a lot of H2O, but it also has some deuterated water and finally some doubly deuterated water. And we were able to measure all of them. These are our values. We got 5 times 10 to minus 4 for the D/H in water, and for the doubly deuterated to singly deuterated we got roughly 1%, which is very high. But it corresponds very well to what you observe in molecular clouds here. Now what can we learn? Water is probably inherited as water ice from the pre-solar cloud. There is now a paper by Furuya. He has a model which shows that if water is reprocessed in the solar nebula, then this value here, so this ratio of 2 ratios should be close to the statistical value of 0.25. If it's much above 1, and in our case it's 17, then it means the ice could not have been reprocessed, because the doubly deuterated water you can only make in the pre-solar clouds and not in the solar nebula. So water is, at least a big part, is inherited as water ice from the pre-solar cloud. We now have a very big variability in the D/H. You see here the protosolar nebula at 1.5 times 10 to minus 5, then the Earth 10 times higher, some meteorites here, and then we have all the comets. And before 67P, it was clear Oort cloud comets were all around 3 times 10 to minus 4. But we had 2 values for Jupiter family comets which were almost terrestrial. And then came 67P, which was much higher. And so that probably means that comets, independent of their family, were formed over a large range in the solar nebula, not all at the same place. If they have a high D/H, they probably were formed further out. And then the family is only determined by the dynamics they experience, by the gravitational pushes they get. They either go to the Oort cloud or they go into the Kuiper belt.
Do you have evidence for temporal variability of D/H in 67?
There is none. It's published now. It's the same. That was at the beginning. We had that. We did it again. It's in Philosophical Transaction. Sorry for that. I had to deliver an article to them. It's now out, and it's still 5.3 a year later, or 5.25. But no, there is no temporal variation here. It stays constant. And finally, of course, the Earth did not get the bulk of its water from comets. I think that's safe to say. Now, in our zoo, we have animals. And first of all, we have butterflies, some very nice butterflies. We have, for the first time, detected the N2. This is very difficult to detect from remote sensing, so that's why it was never detected before. It does not mean that this is the only comet with nitrogen, but it's the only comet where we really saw it. We found O2. O2 is a mystery. And then we found a few others: hydrogen peroxide, carbon monoxide, carbon dioxide. What's in white has been detected before in other comets. What's brown has been detected for the first time in 67P. Now, what can we learn from this here? Comets were probably never warm. Otherwise, they would have lost these highly volatiles. Probably also that comets cannot have been part of a bigger object. I know there are other opinions as to that. If they can keep their very volatiles, if they are formed in a big object. But comets must have formed somewhere around 25K to trap the amount of very volatiles we have. And as I said, O2 is very puzzling because O2 is very reactive. It reacts with H. And so it should no longer be there. It should all have reacted away. And our explanation is that it was enclosed in the water ice, which survived, which we know that it survived, from the pre-solar stage up to today. And I know there are other explanations for the O2 coming from here and coming from elsewhere. I don't want to discuss them here and now, otherwise we would never end. Now we have a few more animals. We have tropical fish. These are the halogens, plus phosphorus. Phosphorus, I don't know what the parent is actually, because all the parents are somewhere at the bad position in the mass spectrum. It could be pH3, I don't know. Then we have the poisonous ones. As you see, we also have a cyanogen that's a chameleon. It's a chameleon because it always tried to hide from our eyes. So it was very good at hiding behind the other peaks. And finally, we have also measured some refractories, which do not sublimate, like sodium, potassium, silicon. And these refractories we measure mainly at the very beginning of the mission, in the first 3 months. And that's sputtering by solar wind, sputtering from the surface by the solar wind. So what does it mean? Before Rosetta, we all thought that cometary ice contains simple molecules formed in the gas phase, and that's certainly true. It contains these simple molecules. And the refractory part is made out of refractories, magnesium, silicon, iron, and so on, and that's also true. But we were able to actually measure the silicon isotopes from this sputtered silicon, and we found that it's depleted. It's depleted. That's a 3-isotope plot here. That's, what is it, 29 and 30 here. The delta notation, so it's how much it deviates from a standard. And you see the mean value is here, solar would be here. It's not 2 sigma, it's just 1 sigma, but it seems clear because here we have the C13 to C12 for CO, and that's also mass 29 and mass 28. And this is exactly solar here. So it's not an instrumental effect. That probably means that the solar nebula was not homogenized. It must have been somehow heterogeneous. Otherwise, comets would have a silicon isotopic ratio distribution like the Sun. Then we have the smelly molecules. You see here the stinky ones, hydrogen sulfide. These are all the sulfur-bearing species. But we also have more sulfur-bearing species. We have S2, S3, S4, metanthiol, etanthiol, thioformaldehyde. And that's a swamp because I think etanthiol smells like decaying vegetation. I read, and S2 is bluish, S3 is reddish, orange, and S4 is reddish. So this gives you the dart fog up there. Now, sulfur is a mystery. Sulfur in the interstellar medium is there as a cosmic abundance, 1/27 compared to oxygen. And then in dark molecular cloud, sulfur is missing. And it's missing quite heavily by several orders of magnitude if you look at dark molecular clouds remotely. Now in comets, the sulfur is back. Comets are not depleted in sulfur. They contain their cosmic abundance. But they contain these S2, S3, S4, probably higher S is 2, but they are not volatile, so we could not measure them, and they are outside our mass range probably. And these species can only be formed on dust grain chemistry, radiolysis of H2S. So it's now assumed, or there is a paper by Woods and others, that these refractory sulfur, S8, is on the dust, and it seems to be quite a lot, and you cannot see it by remote sensing. And that's why it's depleted in dark molecular cloud. It's there, but you don't see it. S2 is very volatile. It has a very low sublimation temperature, and it actually came out already at 3.8 AU. We saw it, S2. There is a refractory part, so once we got closer to the sun at 1.5 AU, we had all of a sudden a higher S2 relative to H2S. But there is this very volatile S2, and S2 is very easily destroyed in UV, in not so high UV. So it's not shielded by hydrogen, because the energy needed is below what the hydrogen absorbs. And so it has to be assumed that S2 does not survive in the gas phase. But it's there. Again, that means that S2, the ice must have survived through the formation of the solar system as ice and not as gas. What else do we have? We have the giraffes. These are long carbon chains, up to 7 carbons, saturated carbon chains, single bonds. So this is a whole lot of CHs. But we also have elephants which are the aromatic compounds. We have benzene, toluene, benzoic acid, and naphthalene, as you see. And probably there is more there. Then we have the whales, the big ones. The macromolecules, that's not from our instrument, but that's from the dust mass spectrometer for dust, COSIMA. They saw a lot of CH, and they attribute it to macromolecules, organic macromolecules. Something like the insoluble organic matter, but not exactly. Then we have the funny animals, the alcohols. You drink ethanol, but we have alcohols up to pentanol, 5 Cs. We have what is it? We have the exotic birds. These are molecules where I don't know where to put them. So ethylene glycol, propylene glycol, I think it's antifreeze, but the Comet is frozen. Anyhow. So hydrocarbons, we have these long carbon chains, like the macromolecules. This is also seen by Wirtis, the black stuff on the surface. The Comet is black, so Wirtis claims that this is carbon-bearing compounds. And we have the aromatics, and we have the complex organics with the oxygen or with nitrogen. That's also seen by Kozak and Ptolemy on the ground. When they landed, they didn't have much data, but at least they could conclude this. And they are certainly more complex than anticipated. And it's a large amount, it's a lot. Otherwise we wouldn't see it. Now in our zoo we have zebras. Zebras, they smell of horse manure. You don't have horses in a zoo, so it's a zebra. And as you all know, lions feed on zebra. So if you take methylamine and CO2, you can form glycine, amino acid, without having liquid water. And it's the only amino acid which you can form without having liquid water. And actually we found it. We have the lion here, who was feeding on the zebras, and we have the glycine. However, comets certainly do not contain life, that's for sure. It's way too cold. Measurements of Miro gave temperatures of 30 K away from the sun. So you have no chemical activity. Probably you don't have biological activity, that's for sure. So we didn't see anything crawling around, but we didn't expect to see anything. But of course, if you then throw the comet into the ocean, then the molecules will become mobile, they can react with water. And maybe that's how finally life evolved on our planet, start from organics, go to RNA, DNA cells, and finally to animals, land animals, and the humans. And I always find it fascinating. We are on top there and looking back to our own origin, which is quite something. There is one more animal here missing, and that's a peacock. A peacock that's useless. A peacock is solitary, but it's certainly noble, and these are the noble gases. We have found argon, krypton, xenon, and we have found their isotopes. The question, did comets bring the Earth's atmosphere? They didn't bring the bulk water, we have concluded that, but they still could have brought the atmosphere. And there is a problem here with the atmosphere because water you can replenish. If you can replenish the noble gases just by the Earth itself, that's questionable. So noble gases, the answer is given by 67p. The abundance of argon, we found out that this is very well compatible with a delivery by comets in the late heavy bombardment. So that's, that fits. And with this, you don't really change the water because it's just about 1% of the terrestrial water you bring when you bring all of the argon of our atmosphere. Comets have a lot of argon. Argon 36, argon 38, of course not argon 40, which is a decay product. And probably the clue on a quantitative assessment, how much comets did actually hit the Earth to bring these molecules, the clues are in the xenon. We have measured 7 xenon isotopes with their relative abundances, and we have evaluated that, and the result you can see this week in Science on Friday. So it's under embargo, and as I'm videotaped, I will not show it, but you can read it on Friday. And finally, our newest animal, these are black bears. You know the comet is black, I told you before, and we have, shortly before end of the mission, we got a big lump of comet into our instrument. It almost killed our DFMS. We saw it very clearly in COPS. And the JADA, the dust flux analyzer, got more dust in this single event than it got over the rest of the mission. So it was really a blast of dust. We were at 2 kilometers above the comet surface. And if I look at our data, I see all these here. We see a lot of CHs, CHO, CHN, CHS, CHON, CHOS, CHS2, and many of them must be unsaturated. So it's not, we cannot explain our spectra just by taking the saturated molecules. That's investigation ongoing, but I think it's also quite interesting if you look at most of them, they go down with mass. Except the CH, it goes down with mass, but at the C6, it stays constant. And that's probably all the aromatics. Again, unsaturated aromatics. So that's our black bear. And that's how the spectra look. You see we have a lot of peaks, and that means a lot of work. So back to our sketch. With the help of 67p, we can say something about the interstellar medium with the isotopic ratios of silicon and xenon. We can say something about molecular clouds, something about the star-forming region, solar disks. We can say something, temperature, about the protoplanetary disk, about our Earth here, the DOH, the water on our Earth, and finally probably also something about the origin of life by looking at organics and again at the isotopic ratios of the noble gases. And that's very satisfying. I think we have done a good job deciphering the origin of the solar system just by looking at one tiny little comet. It's one, which is a very bad statistics, of course. But Rosetta has more than achieved its goals. You see the number of publications, it's still rising. And it should not be the last step. We have to go on. And we have analyzed roughly 90% of our data, so there is still work to do for many PhD students. But then we have to start planning, and we should do it now before. It took 30 years between Giotto and Rosetta, and that was way too long. People by that time had forgotten what the comet is. So we should go to another comet. We don't need the full complement of instruments, so we can make it smaller. It's probably an ESA M mission size. Visit the main belt comet to compare. I think that's also an ESA M mission size. Then again land on the comet. I think we missed with Philae, we really missed going down through the surface. And there was once this Comet Hopper mission here, and we should probably do that again, but really do it and not stop in the mission in the middle. Land and hop and dig, and then bring back a refractory sample. That's under evaluation as far as I know here, but it will be refractory mostly, and not the ice. And the goal of the workshop, that should be the goal. Bring back a cryogenic sample where you can really study it with all we have in the labs, which is even better than Rosina. Rosina was great, but I think we can do even better here. So an artist at ESA drew my Sioux up, which I find very nice. And what you see here is some tails, some ears, and these are the animals we have not yet found, but we have signs of them, which in mass spectrometry means we have fragments, which we cannot attribute. So this Sioux will grow in the future. And with this, I stop here. Thank you very much.